Hi everyone, this is Dr. Nigro with the Chem Calculations screencast. This screencast is going to add on to one I did earlier that focused on electron configurations and orbital diagrams of neutral atoms. This one is going to specifically look at writing those configurations or drawing those orbital diagrams for ions. So if you need to understand the basics of how to write out an electron configuration, please make sure you go back and watch that earlier video, because that earlier video is going to have you look at how to use the periodic table to write the electron configuration themselves and how to write the shorthand or noble gas configuration for these elements. This is going to focus on what's the difference between a neutral atoms configuration and an ions configuration. All right, so let's start with the word ion. So remember, for ions, we've either added or removed electrons from the most energetic sublevel in that atom. All right, so ions, they have to be charged. All right, so these are not neutral atoms. These are atoms that have lost or gained electrons. Now remember, we've defined a cation as a positively charged ion, which means that electrons have been removed. All right, and our anion is our negatively charged ion, which means electrons have been added. Now we're not going to get into where these electrons are coming from or where they are going in this video. That's beyond the scope. And that's going to be more vital or important when we talk about bonding. But we're just now going to remind ourselves of those definitions. All right, so we're going to do two quick examples just so we can see. All right, so let's look at fluorine neutral electron configuration. So we start at the beginning of the table, and it's 1s2, keep moving, 2s2, move across 2p, we count over 5, so that will be our electron configuration for fluorine. Now, fluorine as a halogen likes to form -1 ions, so what would the configuration look like for a -1 ion? So we start with the same core, and then when we get to this 2p sublevel, instead of having 5 electrons, it's gained 1 electron because of that -1 charge, so that 5 becomes a 6. So it's 1s2, 2s2, 2p, 6. All right. What if it's the other situation? Let's say we have sodium. All right, so we write the neutral electron configuration, 1s2, 2s2, 2p6. We come down to row 3, and there's sodium, so 3s1. All right, well, sodium as an alkali metal likes to give away electrons or donate them, so it forms +1 ions. So we start again, 1s2, 2s2, 2p6, and when we go from the neutral atom to the ion, we have lost 1 electron. So that 3s1 electron is gone. All right, so we just write it 1s2, 2s2, 2p6. All right, now for those noble gas configurations, you're going to do the same thing. You're going to remove or add, all right, and then, whoops, not but, then rewrite new last row. All right, and you'll see what I mean in just a minute. It's easy, particularly for the cations, when they lose those electrons, to want to just leave it, the noble gas in brackets, and that be it. But you really need to move up a row. All right, so we'll look at a couple of those. All right, for our orbital diagrams, we're going to remove or add from, whoops, sorry, it's a terrible from. Outer orbitals. All right, and we need to remember to follow the filling rules. All right, and again, if you need to go back and watch that other video, those filling rules are the off-bow principle, the Pauli exclusion principle, and then Hund's rule. So make sure you understand what those are. All right, so let's look at these electron configurations. All right, so let's start with chloride. All right, I'm going to start by writing chlorine. So 1s2, 2s2, 2p6, 3s2, and then 3p5. All right, but chlorine has picked up an additional electron. So where am I going to put it? Well, the filling rules tell me I need to put it in the outermost shell as long as there's space. Well, it's 3p5, so there's still room out here. So the electron configuration becomes 3p6. So there's our additional electron. It went from 17 electrons for chlorine to 18 electrons for chloride. All right, now let's try magnesium. All right, so we've got 1s2, 2s2, 2p6, 3s2 for neutral magnesium. But this is a +2 ion, so that means it has lost 2 electrons. So I'm going to remove those electrons from the outermost sublevel, which means that my 3s2 electrons are going to go away. All right, so we go from 12 electrons to 10 electrons. Okay, now chromium. All right, let's do chromium's electron configuration first. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. And let's count over. 1, 2, 3, 4. 3d, 4. So that's neutral chromium. All right, but this is a +3 ion. All right, the transition metals, as in many other areas of chemistry, are a little tricky. All right, that 4s sublevel and that 3d sublevel are very similar in terms of energy. All right, so what the transition metals will do is lose the s electrons first, and then any remaining electrons can be removed from their d sublevel. All right, I need to remove 3 electrons, so I'm going to lose these 2 and then 1 of these. So my electron configuration should look like 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. All right, I know that seems a little strange, but it's just the way those sublevels stack up in terms of energy. The s electrons are held less tightly than the d electrons, so they are easier to remove, so they're removed first. All right, that's only for the transition metals. Don't do that for any other elements. All right, let's do our noble gas configurations for each of the following. All right, so rubidium +1. All right, so for neutral rubidium, I look at the end of the row above, and I've got krypton. So there's my noble gas that represents the electron configuration through krypton. And the rubidium is in row 5, so it'd be 5s2. All right, now rubidium form, no, 5s2, sorry about that, that's wrong, 5s1, whoop, and I erased it all. All right, now rubidium has lost an electron, so it's very tempting to just write Kr. All right, and I can understand that, but that's not technically correct. All right, what you should do is now rubidium +1 electronically resembles krypton, so you need to go up a row from krypton, so we would say argon in brackets, and then we do the row that contains the krypton, so that's going to be 4s2, 3d10, 4p6. All right, so even though the Kr brackets and the argon 4s2, 3d10, 4p6 are the same electronically, it's the better way to write it. All right, so let's look at phosphide. All right, so we look at phosphorus, we go up a row, whoops, and we have neon, and then we write the configuration for the row we're in, 3s2, 3p3. All right, now we're going to gain 3 electrons here. All right, it's actually a little easier for the anions. So what I'm going to do is just rewrite this and put those 3 electrons into that 3p sublevel. So it becomes 3p6. All right, do not just look at the end of that row and write argon. All right, you need to write the noble gas on the row above, and then that particular electron configuration. So you should never have just brackets with the noble gas in it. All right. All right. Now we're not going to do the silver ion. I know it says silver, but instead we're going to do iron, and we'll do the +2. Well, let's do the +3. So Fe +3. All right. So we look for iron. Where are you, iron? There you are. All right. So argon. And then for the row, it's going to be 4s2 and then 3d, 1, 2, 3, 4, 5, 6. So this is neutral iron, all right? It is a transition metal, all right? So that means s electrons first. So we're going to lose these two and then one of these, all right? So I'm going to rewrite that as argon 3d5. So that would be the electron configuration of iron +3. Okay, now, using these noble gas configurations, draw the orbital diagrams of these non-core electrons. All right, so for rubidium, I'm going to have argon, and then I'm going to have 4s, 3d, and then 3, oh, my 3p is not that good. Hold on. Spread those out just a little bit more. There we go. All right, so I have 4s2, so I'll fill these in. And then I have 10 electrons in my d sublevel. Remember, the up and down arrows tell us opposite spins, which is required by the Pauli exclusion principle. And then out, oh, you see a mistake I made here? This is not 3D. This is, 3p. This is 4p. And it has 6 electrons in it. So that will be the orbital diagram for the outermost electrons of rubidium +1. All right, for phosphide, we're going to have neon in brackets, right? And then we have the 3s sublevel and then the 3p sublevel. All right, and we have 2 electrons in the 3s and we have 6 in the 3p. So that's what our orbital diagram would look like for phosphide. All right, and then again, we're not going to do silver here. We'll do the iron +3. All right, so we're going to have argon in brackets, and then this time you can put the 4s in if you want. You do not have to. You definitely have to have the d. All right, because we're not going to put any electrons in that 4s sublevel. Instead, we're going to have 5 electrons in the 3d, and according to Hund's rule, we're going to put 1 electron in each orbital before we pair them. So our orbital diagram will look like this. Okay, so again, for ions, when you're doing the electron configuration or the orbital diagram, you are just either adding in electrons for your anions or removing them for your cations. Please remember the transition metals require removal of the outermost s electrons, and then you may start taking out of the d. Okay, that's really the trickiest part about the ion electron configurations. Okay, again, if you need more help with just writing general electron configurations or filling in those orbital diagrams, please go back and watch the screencast that focuses on those 2 topics for neutral atoms. That'll give you some help. Okay, thanks.